Hi, Subir, can you hear us? I think he's. Sorry, you're on mute, Subir, I think.
All right, can you hear me?
Yeah, perfectly. Thank you. Yeah.
Okay, great. Okay, so good morning and good evening. Hope you can all hear me clearly. So we're continuing the discussion of the electron Hubbard model, defined here with on-site interaction U and hopping T. So this is the basic phase diagram. At very large U, you have basically very trivial phases in a sense. So this is the empty phase with no electrons. This is the region with exactly one electron per site. And we discussed how in a strong coupling expansion, we can see that there's antiferromagnetic order of the spins. So we call this an antiferromagnetic insulator. And so here the density is 0, the density is 1, and then there's a region with density 2, where you have a band insulator. So these are all extremely well understood phases. And we are interested in what happens when you vary the density from these very special values. So that's the rest of this phase diagram. And at very small U, it's a Fermi liquid with a Fermi surface. And really what we want to understand, and it's important for many, many experiments, is how you go from the Fermi liquid here to the antiferromagnetic insulators. So what I presented so far is last lecture was this green arrow, and that's what I want to complete the discussion of this morning. What happens when you put in a small number of holes, you reduce the density a little bit. So the density is 1 minus P. And what do you get? Well, experimentally, we know that we get a D-wave superconductor. And so I'm just presenting a so-called vanilla theory of how this happens, starting from the insulator. So what we argued is that as long as you're at large U, then you can map the system onto a TJ model. And there's various other terms that I haven't written here. So there's the same hopping term that you had in the Hubbard model with this extra projection operator. So this is, of course, part of the difficulty of the problem. This projected insists that you only look at matrix elements of these operators within the subspace where there are never any doubly occupied sites. Then the interaction term we wrote in this way. This term preserves the number of particles in every site, since there's always a dagger J and an undagger J here. So you don't need the projection operator as such. And you can think of this as a Cooper pair number operator, where this is an operator that annihilates a pair of electrons in a singlet bond. And that's what we're going to call a Cooper pair here. All right, so that's the Hamiltonian we'd like to solve, and we're not anywhere close to solving it. But we are doing now a vanilla theory of it, where we do two things. One was we just ignore the projection here and replace this hopping term by some dispersion EK, which let's assume we measured it in experiments, in a photo emission experiment. And this particular term, you just factorize. You replace one of these factors with an expectation value, which I call delta X and delta Y, depending on whether it's a vertical or horizontal bond. And then when you take a Fourier transform of the remaining terms, this is the Hamiltonian that you get. which is now finally in a form that only has pairs of fermion operators, and so can be exactly diagonalized, which is what I want to complete today. And that this second procedure here is the BCS, or the Bogoliubov calculation of the theory of superconductivity. The only difference from the original calculations is that this delta here depends on K. In the original electron phonon picture, where we have what's called S-wave pairing, then you can just ignore the K dependence of delta, it's right. So there's only one number delta. Now we have two numbers to worry about. But other than that, it's not essentially different from the original BCS theory. All right. Any questions on that summary? Okay, and I also should remind you that there's a second problem set which is in the works. I don't know if it's been circulated with the students yet, but if it's not, hopefully in a day or so, you'll get it. To involve things I'm going to discuss today. Okay, so the first course of action today is to just diagonalize this Hamiltonian and complete the story of what is a D-wave superconductor or any superconductor. And then I'll start what's labeled here by the red arrows, start from the Fermi liquid side rather than the insulating side, and think about the same phases. In particular, how would you get a D-wave superconductor starting from this side, and also a metallic phase, which has the same order locally, but it's a metal rather than this state, which is an insulator. Right. So these type of calculations were also done in the very early days of ITC superconductivity, and what I'll present today are things that are well understood, at least known for a long time ago. But just understanding ultimately how these three phases interplay with each other is really the heart of the problem. That's involves, it's not anywhere close to being solved, and I'll talk about more ideas about it as we go on. But yeah, once we're done with this, we'll have done with the traditional part of the course, where the common theme really is mean field theory, that you take whatever complicated Hamiltonian you have, and you factorize it in a way you get the simplest possible, well, you get a free particle description. And in that free particle description, there's a number of parameters, and you optimize it. And just doing that, is the story of essentially all of condensed matter physics, and for quite a while, and been extremely successful until in the 80s it started not working so well in the cuprates and other materials. All right, so but let's continue on that traditional task today. Definitely by next week we'll get to the more modern era. All right, so we just have to diagonalize the vanilla BCS Hamiltonian. And in this case, that's easy to do by a unitary transformation. You do a canonical transformation of the fermion operators, and that in this case turns out to be a unitary transformation. CK up, C dagger minus K down, divided by a 2x2 matrix, which is a unitary matrix. And it's conventional to use these symbols for them. UK star UK, VK minus BK star, and gamma up, gamma dagger K down. We introduce a new set of fermion operators, which are the Bogoliubov operators, which are also fermions. And unlike the case for bosons, where it was a bit more subtle, in fact, when you do a unitary transformation, meaning these objects here obey the relation UK squared, that's BK squared equals 1, then you'll find that given the commutation relations of these objects, which are free fermion, right, that the gamma also have the same commutation relations. So they're also ordinary fermions, and they carry spin a half. And this whole thing preserves spin rotation invariance, also although the notation doesn't make that completely evident. All right, so now you have these three parameters, UK and VK, and you insert this, this operation into the vanilla BCS Hamiltonian, and you choose the UK and VK cleverly to get a very simple Hamiltonian. And the final Hamiltonian it just turns out to be equal to someone K, EK, gamma dagger K alpha, gamma K alpha plus some constant. And it determines UK and VK in terms of all the parameters, the Hamiltonian. I won't write out the equations, they're in the notes and you can look them up. And in particular, EK got to the square root of epsilon squared plus modulus of delta K squared. Okay, so now you're, you have everything you need to solve the problem. You pick some values of delta X and delta Y. You then compute this answer, and you compute UK and VK. I haven't given you the expressions here. And then you compute the right-hand side in this Hamiltonian. Since this is a free fermion Hamiltonian, it's easy to compute that. So that whole procedure gives you a set of equations for delta X and delta Y, which in fact, maybe I can write out. So when you close the circle on these computations, you get a set of equations for delta X and delta Y, and they turn out to be the following. So this, all of this implies, this yields cosine kx, 2ek, tanh. You can do this at finite temperature also, and similarly with the x close to y. It's exactly the same, except you replace this like ky over there.
Is that meant to be epsilon k?
This is capital EK, I think it's okay, which is this number here. So that is the, this is the energy of the quasi-particle excitations, and this tanh simply comes from the Fermi functions of those quasi-particles. Okay, so now you have to solve these two equations, so delta X and delta Y, and then you really have to keep track of this constant and pick the solution that has the lowest energy of free energy. Yes, was there some question there?
Yes, I have a question. So how do you choose the spin of gamma operators? Because they seem to be some linear combination of up and down spin.
Well, there are two operators, gamma up and gamma down. And I've written the operators C up and C down in terms of gamma up and gamma down. Okay, so by this relation, so this you can regard this as a postulate, but then you can ask, what is the spin carried by a single gamma dagger excitation above this ground state, and that will turn out to be spin a half, although that requires a little more computation to figure it out.
Okay, thank you.
Yeah, I mean, if you know a little bit about spin rotation, you can think of this. This is very much like a spinner. It's not up and down. If you want to write this in a rotation invariant way, you would write it something like this: gamma k alpha and epsilon alpha beta, gamma dagger minus k beta. So that would be the, then everything is explicitly spin rotation invariant, because this epsilon alpha beta is an invariant tensor under SU2. So that's basically what's been done here. You can check that this object has exactly the right. So this gives you the upper component of this. And you can check that this object has exactly the right rotations to be consistent with spin rotation symmetry. Okay, so the gamma particles, carry spin a half, but their charge is uncertain because you're mixing together C and C dagger. If you invert this relation, gamma mixed together C and C dagger, but the coefficient involves U of K and VK. And one of the things you find when you do the computation that the off-diagonal term VK, is proportional to delta K constants. And the relationship then is gamma K is something like UK CK plus VK C dagger minus K. So here it looks, you're removing an electron. That's the gamma K operator, but there's another term where you're adding an electron. But the VK is proportional to delta K. And if you remember, the delta is a Cooper pair annihilation operator. It removes a pair of electrons. So you're adding an electron here and you're adding and removing a pair of electrons in here. And so that's why, at least formally, particle number is conserved. But the gamma K is a linear combination of two processes. One which you remove an electron, and the other where you remove a Cooper pair and add an electron. And you have to consider both. So electrons are not disappearing anywhere. They're just associated with these factors of delta K. But you don't keep track of whether you removed a Cooper pair or added a Cooper pair because there's a condensate of Cooper pairs, which is a very large number. And that's in fact the very next topic to discuss what is the ground state wave function. Okay. Right, so what I was saying earlier was you have these equations you have to solve. And of course, one solution is delta X equals delta Y equals 0. That's always a solution of this set of equations. That would be just, you go back to the Fermi liquid then. But that's below a certain critical temperature, that's not the optimal solution. Then you can get delta X and delta Y non-zero. So the solutions of this equation, one is delta X equals delta Y equals 0. The other one, so that's the metal, of course. Then there's a solution where delta X equals delta Y, and that we call the S-wave superconductor. And another solution, delta X equals minus delta Y, which is called the D-wave. And then you have to, take these three solutions, plug it in here, look at that constant, and find the one that has the lowest free energy. And below a certain critical temperature for these equations, this third answer is the one with the lowest free energy. Something that was, I guess, in this context, pointed out first by Kotler and Liu in the late 80s. And then we'll see later how even the other computation gives you pretty much the same answer. All right, so what I want to do before closing this
Is there a range
session,
of parameters where you find the second solution?
not for this particular model. I think if you put in second neighbor exchange or various other interactions, then you can get the other one. So in the Nick type compounds, you get some strange mixture of these things. It's very complicated, and that's for taking different band structures and different sets of interactions. So the answer, which is lower, is kind of a delicate one. In the end, it depends on the nature of the interactions and also the shape of the Fermi surface. And that's not so evident from this calculation, but that will become more evident, if not today, by next lecture when I talk about the approach from the Fermi liquid. But one thing I want to do now, before turning to that, is to look at the structure of the ground state. What is the ground state wave function? And that pretty much follows from this rotation and the fact that these numbers are always positive. So it's clear that the ground state is the state gamma k up, gamma k alpha, are both spin up and down, acting in the ground state give you 0. So it's the vacuum of the Bogoliubov particles. All right, so what is the vacuum in terms of the vacuum of the C particles? So this is some state which is annihilated by the Bogoliubov operator. But the state that we know is the empty state, which is annihilated by the C operators. There's no particles in it at all. So we want to relate G to O. And you can do that by just playing around with this relationship and check that the answer is the following. So G turns out to be product on K. I think the homework is solve a problem like this for bosons. In fact, the answer for fermions is even simpler. It turns out to be C dagger K up, C dagger minus K down. So this is the famous BCS wave function. In fact, BCS presented the theory starting from this point and going the other direction. I've kind of gone exactly backwards by just factorizing things in the Hamiltonian. And then you find that this is the ground state that ensures this is true. You can just check by, once you need to know it works. You have to, this minus sign is crucial. Just work through it and you'll find this is the answer. Okay, so that looks kind of mysterious. It says that you take the empty state and you add pairs of particles at some equal and opposite momenta and opposite spin, and every time you add a pair of particles, you get a decay factor. But this wave function, is already rich enough to describe the Fermi liquid in addition to the BCS wave function. So for example, in a Fermi liquid, if you had no pairing, if you took the solution delta x equals delta y equals 0, and then you looked at the values of Vk and Uk, what you would find is that Uk, as a function of momentum, okay, this is Uk would be 0 up to the Fermi wave vector, and 1 above it. So this is UK, and VK would do the opposite. And then that way. And you can see that this wave function is nothing but the wave function of a Fermi liquid. It's just product on K, C dagger K up, C dagger K minus K down. This is exactly the Fermi liquid with K less than Kf. You have a Fermi sphere and you occupy all particles inside the Fermi sphere. All right, so that's the trivial solution. And now you have to look at what does this wave function look like when delta x and delta y are not 0. Okay. So to write it out, it's actually fun to write it out in a different way. I'm going to play a few tricks. These are all, at this point, all exact manipulations.
Sorry, which curve is UK and which one is VK?
Sorry, this is VK. The orange curve is VK. So VK is 1 and then 0. And UK is 0 and then 1. Okay. So above the Fermi level, you don't add any particles. And below the Fermi level, you add them in pairs. But that doesn't mean much. I mean, you can always rearrange all these terms. It's an ordinary Fermi.
Sir, one question, I mean, that in the pi, will it be mod k less than kf? I mean,
Yes, absolutely. Thank you. The vector, yeah. And of course, if you work out the answer for the D-wave superconductor, then you'll get a curve that looks like this, but has some window of energies where, so this is in the superconductor. And the fact that there's a region here that both UK and VK are non-zero that's what breaks the symmetry. That's what gives you a superconductor. You need some region of momentum space that both UK and DK are non-zero. And okay, that'll become clear by some manipulation of this wave function. So first of all, all right, so I'm going to take the same wave function and play with it. So I'm going to rewrite it for now as product of K exponential apart from some normalization. So it's proportional to exponential of VK over UK C dagger K up, C dagger minus K out. Acting on the empty sphere. Okay, so this is again exactly true because the square of this operator is 0. Because once you try to add in any K state more than one fermion, you get 0. The square of this operator is 0, so this is exactly equal to this, apart from this factor of product of K UK, which you can pull out. Okay. All right. Then next you notice is that these at different K, this particular combination commutes with the other operators. So C dagger K up, C dagger minus K down commutes with the C dagger for other K. So because of that, I can now take this product and put it inside the exponential. Okay. All right, so that's now my wave function. It has an uncertain number of particles. It's exponential of this just one operator. And what is this operator? Well, this is the operator that creates a pair of Cooper pairs. And the values of delta X and delta Y will tell us what this looks like. So what I'm going to do now is just take just project out the term in here that reserves the total number of particles. So let's imagine we have a total of n particles. This is just the same as going from the grand canonical ensemble to the canonical ensemble. This part is essentially exact because the two ensembles are the same for a big system. So n is the total number of particles. So my ground state now in the canonical ensemble is just this object, BKUK, C dagger K up, C dagger minus K down, to the power of n over 2. And now you're starting to see why this is essentially a Bose-Einstein condensate. If you wish, I can rewrite this in position space. So you can think of this as the following object. In position space, it's the integral dr1, dr2. You take a pair of particles at positions r1 and r2. You have some wave function g of r, g of r1 minus r2. And you add an electron with spin up at point r1. Add an electron with spin down at point r2. And you take the n over 2 power. So you have a pair of electrons at positions r1 and r2. And whenever you add the pair of electrons, their internal wave function, their relative wave function is g of r1 minus r2. And this g of r1 minus r2 is of course nothing but the Fourier transform of Vk over uk. So g of r K, Vk over Uk, e to the I K dot R. And in fact, yeah, hopefully I even have the full expression for Vk over Uk somewhere, I hope.
Right.
Yes.
Is there any issue with the fact that UK can be zero? I mean, the manipulation you sort of divided and so on.
Yeah, so once you're in the superconducting state, then UK is non-zero for all K and Bk.
Okay, just exponentially smaller.
It falls over the power law. No?
Power.
The exponential decay is in the R dependence, not the K dependence. Yeah, so these expressions are in the notes, and I hope I can find them. I wrote them out explicitly here. Well, okay. So this turns out to be. All right, also there you can simplify this, but I can give you the answer. So this is equal to integral over K, cotangent an angle phi K times e to the I K dot R and sine 2 phi K is equal to then this. There's an overall sign that I have to worry about. Yeah, all right. Yeah, mod, so it's mod delta over square root of epsilon k squared plus delta k squared. So this is the kind of expression you get. All right, I may not have got exactly the right expression, but the important thing about this is when you take the Fourier transform, is that it has some decay over a length scale, which is given by the inverse of the energy gap. Although when there's gapless nodal point that I talked about yesterday, then there's kind of a power law tail that I won't worry about. And also the other important point is this G of R, when delta x equals minus delta y, as a function of vector R, has the form of a d-wave wave function. So when delta x minus delta y, then as a function of the angle, this is the famous d-wave wave function. So this, what are you plotting? Yeah, so this is the famous d-wave wave function where you're plotting. Yeah, so this is G of R, plus here, minus here, minus there. So when the pair separate in the x direction, you get a positive wave function. When they separate in the y direction, you get a negative wave function. And that just comes from putting in this and taking this Fourier transform. All right, so now what you see here is that this d-waveness is really something having to do with the internal wave function of the Cooper pair. There's a Cooper pair, and there's two electrons in the Cooper pair. The Cooper pair is not a point object. It's got some spatial extent. And the two electrons in the Cooper pair are in a state that has some non-trivial angular momentum. In this case, d-wave with delta x equals minus delta y. It's not degenerate because the presence of the square lattice, the d states are not, at least this particular state doesn't have a partner that has to be degenerate. Right, but the superconductivity itself, suppose that this is the ground state for this superconductor, but what would be the state when I have a current flowing, when I have a state that has some phase variation that we saw for the case of the Bose-Einstein condensate? What would that be? So that would be the state, if I had something with a current flow, a state with got some current J, then there'll be an extra phase factor here, inside. There'll be a phase factor inside here. Will be some center of mass momentum, P dot R1 plus R2. All of superconductivity and its phenomenology of superflow at long distances has to do with the sum of the coordinates whereas this internal D wave nature has to do with the difference of the coordinates. So this, also shows that, in fact, the BCS wave function is nothing but the Bose-Einstein condensate of Cooper pairs. It's exactly the same wave function, although for some mysterious reasons, there was a long period in the 60s where this was debated and argued whether they are really different phenomena. They aren't really. It's pretty much the same thing. That the theory of a weakly interacting Bose gas is not any different from the theory of low energy collective excitations of a BCS superconductor. And all the issues of broken symmetry and superfluid stiffness that we talked about transfer here with no change, except the change here is the boson is not a point object. So when you have to refer to the center of mass coordinate of the boson to get it, to map it onto the theory of Bose-Einstein condensate.
Subir, could you just provide us some understanding of when you get the S wave and when you get the D wave? Is there some difference in the microscopic structures?
Yeah, so I think I'll defer that question probably to next lecture. It's much easier to see that starting from the Fermi liquid approach. But the short answer is it depends on the nature of the interactions between the particles and also depends on the shape of the Fermi surface. And there's a lot of possible answers depending upon the shape of the Fermi surface and the nature of the interactions, whether it's spin dot spin or density dot density and so on. Yeah.
But the formula for the ground state that you've written here is general.
Yeah, everything here is completely general for general delta K. And these equations that I wrote down are also general. They're just a little, well, you could work with those equations and get the answer. But it's, yeah, I'll just defer it. I will discuss precisely this question.
Sure.
Yeah. Yeah, Nati, go ahead.
So I assume that if delta x equals plus delta y, it's kind of more spherical.
That's right, yeah.
And what's the characteristic scale of these two features? So there's a length scale associated with.
Yeah, so there's a length scale here, which is basically called the coherence length. And it's basically the Fermi velocity on the Fermi level divided by the magnitude of the gap on the Fermi level.
And what is it in practice?
So in the old superconductors, it's about 1,000 angstroms, so it's very big. And that's really the reason that BCS theory is actually very quantitatively accurate. In high TC superconductors, it's only about 3 or 4 lattice spacings. It's not that big. And that's why, that's one of the reasons why we can't just think of it as, think of this in the mean field theory. There have to be other corrections.
And is there a difference between the S wave and the D wave in terms of the characteristic scale?
No. But when you take this Fourier transform, if there's a 0 here, then if the dispersion has a 0, if it has a node, then this Fourier transform will give you a power law tail. So it doesn't decay exponentially. There's still this length scale, but there's a tail that has a power law in the D wave case. For the case where you have nodes. Anytime you have nodes, you will get power law tails in the pair wave function. It's just a matter of doing this Fourier transform.
Does this length scale appear in the effective theory, in the Landau?
It appears, it depends, yeah, the coefficients depend on it, correct. And in fact, if you do kind of if you look at thermal fluctuations, which is what Landau and Ginsburg were doing, then you get some 5-fold field theory for it. And then all the coefficients depend on this length scale. And then from the 5-fold field theory, you pick some, what's called the Ginsburg ratio, or you can just think of it as the dimensionless measure of the strength of the nonlinearity. And that parameter depends on C, the Ginsburg ratio. So I can say a bit more on what the Ginsburg ratio is in a modern language. It's really nothing that surprising once you know a little bit of field theory. Okay, let me do it here. I can do it up here. So you take a wave function like this, which has an arbitrary center of mass dependence. So this is just the internal wave function, but you also put in some center of dependence on R1 plus R2. This is all in the notes, actually. So then you will get a free energy. The Landau-Ginzburg free energy is some kind of field theory. Let's say we want to look at spatial dimensions, DDR. Let's make the coefficient 1 plus something R psi squared plus U psi to the 4th. So from these combination, you can make a combination called the Ginzburg ratio, which is U over R to the D minus 2 over 2. No, sorry, not D minus 2. 4 minus D over 2.
Just to make sure I understand, R is not the same R, it's the same formula.
Oh, yeah, no, this is plenty. Yeah.
U is probably not the same thing. You call it.
No, these are very different things. They depend in a very complicated way on the coherence length. Let me make them capital R. Let me call it V if you wish. So V over capital R. So this is a mass. This is dimensions of 4 minus D, as you know. So this is an invariant number. And so this Ginzburg ratio, let's see if it goes as 1 over some C to some power. I forget the power. Or no, wait a second. Yeah, okay, provided you're not very, okay. It's a little more complicated than that. Let me not make a wrong statement. So this is the dimensionless measure of how strong the nonlinearity is. And this number is determined by this coherent length. So at least at 0 temperature, that's quite a very low temperature, is determined by this scale. And it's very small. So this is why BCS theory is. Because C is large, this number G is very small.
And the mass of the Higgs, let's say that's a different parameter.
Yeah, so this is at low temperatures. Now what happens, of course, what Wilson pointed out was that when R goes to 0, then no matter how small V, you have a problem because this number becomes large and then you need the RG. So certainly close enough to TC, BCS theory fails. At least the fluctuations become important. And if you put in all the C dependence, what you find that in the BCS theory, you have to be extremely close to TC, or to part in 1,000 or better, for this Ginzburg ratio to become large. So all the fluctuation effects are completely negligible, thermal fluctuation, except in a narrow window near TC.
Maybe answer my question, but I guess my question is, in this type of Lagrangian, there is a length scale, which is the mass of the Higgs. Or
The mass of the Higgs. Yeah, so that's, let's say at 0 temperature. Yeah, that's also, it's pretty much this gap. Yeah, it's the same thing. Yeah, it's a factor of 2 different or something. I haven't shown that, but you have to do the calculation of fluctuations of delta K. And that gives you the Higgs particle. And it has a mass which is of order 2 delta, in fact. That's at 0 temperature. I mean, the thing is that finite temperature fluctuations near critical temperature are very, very different from what happens at 0 temperature. 0 temperature, there's always a superconducting ground state, and it has a Higgs-like excitation. But to restore the symmetry and get rid of the Higgs is more complicated here, because then the Fermi surface comes in and does various things at 0 temperature.
Is this Higgs very broad here?
It can be because, in fact, it's right at the edge. And usually it could be broad because you can decay into a pair of Bogoliubov quasiparticles. Yeah. In fact, right at the edge, because to create a pair of Bogoliubov particles, you need energy 2 delta. And it seems to be right there. So I think experimentally it has been seen now, from what I understand, but in very special material. If you take a general material like aluminum, you don't see that excitation. It's too broad.
I guess you're thinking here of it as a real excitation. So you need to do it, you need to add time, and then you have the question of whether this is a first order action or second order action. Side.
Yes, exactly. Yeah. So that's why at finite temperature, I can forget that. I just look at fluctuations of the pairing order parameter. But at zero temperature, yes. So what you have to do is what we did for the Bose gas, and which I'm not going to do for antiferromagnetism, is instead of doing mean field theory, you have to use the Hubbard-Stronovich transformation. And you have to make delta a function of space and time of the center of mass coordinates. And then you get some effective theory for delta. If you take that effective theory at near TC, at finite temperature, you can ignore the time dependence and you get that.
Yeah, I guess I was asking a simpler question, which is if you view, if you expand this Lagrangian around, let's say the Bebop side.
Yeah.
Quadratic order, and you look at there's a kind of spatial kinetic term.
Yes.
And there's a mass term.
Right.
That mass term. So
yeah, that's so. What I'm saying is that.
Where is that delta? I guess.
What I'm saying is that at zero temperature, it's a delicate business, and you can't just do it by doing it. This thinking of an effective field theory. You have a trace log over the fermions, and you really have to keep the full trace log to get the right structure. You can't expand the trace log over the fermion determinant in powers of psi. You can do that at finite temperature, near TC, but you can't do it at zero temperature. We're going to see exactly the same issue in a minute for antiferromagnetism. Right. Okay. Yeah, I mean, I'm happy to go into that more detail, but maybe it's not on the plan right now, and I certainly have notes on it. Okay. Any other questions? All right, so actually, those were very appropriate questions. Now we're going to try to address the same kind of, superconducting behavior, but starting from the Fermi liquid. And here, you could again try to do a mean field theory, but in fact, that doesn't work as simply as this works. You have to do some more careful calculations of fluctuations. And so we will have to do a more sophisticated calculation here. And then we'll find not only is there a possibility of superconductor, but there's also a possibility of antiferromagnetism. So that's what I'm going to focus on first, how you go from a Fermi liquid to antiferromagnetic metal. And here, I will also do it in a more complete way, where we'll be able to talk about time-dependent fluctuations and space-dependent fluctuations of AFM. The question that Juan was just asking are all connected to what happens when this delta itself becomes time and space dependent. And you can do the analogous thing also for superconductivity, and maybe later on I'll mention something about it. But let's do it here, which is what I prepared to do today. Okay. So the basic trick is something we already met, in the theory of the Bose gas, which is the Hubbard-Stronovich transformation. And that you can think of as, a way of doing mean field theory that also allows you to look at corrections to mean field theory, to time and space dependent phenomena, and also higher order terms. And you could do the same for BCS, but I haven't done it. All right, so we're going to work with the U term, and imagine U is small anyway. And it's convenient to rewrite it in a different way. I put a -1/2 here. And this is equal to -2u/3 SI squared plus u/4. So this is an exact identity you can check by putting in the fermion operators and using various commutation relations. Or more quickly, you can just look at the states. So this particular term in the Hamiltonian, on any given site I, there are 4 states. There's the empty state. And what's the energy of the empty states? Well, this will be -1/2, that's a -1/2. So as energy, which is 1/4. Then there's the doubly occupied states, where this will be 1/2 and 1/2. And that also has the same energy. So there's the empty state and the doubly occupied state. They both have the same energy of 1/4. And then if you have just one particle, then one of these is +1/2 and the other is -1/2. So that'll be energy of -1/4. This is just either this or that. Okay. And then you can see that this operator has the same object. When the spin is 0, both of these states have total spin 0, gives you U of 4. When spin is 1/2, then S² for spin 1/2 is 3/4. And if you put 3/4 in here, you will get -1/4. Okay, so that's how you can quickly guess this without playing around with commutation relation. All right, so then we're going to take the original Hubbard Hamiltonian and do a path integral. So let's write it out. The path integral over the fermions, C I alpha of tau, exponential beta d tau, sine dagger. Sorry, I'm going to call it C right now. C dagger I alpha. These are Grassmann numbers now. It's very similar to what we did for the Bose-Hubbard model, except these are Grassmann numbers, and that just changes the signs in a few places. Okay. Then there's some dispersion, and we'll just write it out. Let's see, EK, C dagger K alpha, C alpha, dispersion, and then the interaction term, which is here, and that comes in the minus sign. So this manipulation has been done to get rid of that's something with a minus sign here. And the reason we want something with a minus sign is because then the Hubbard-Stratonovich transformation is legal. Or another way to say it is that this interaction is such that it prefers to have, for a certain range of chemical potential, an odd number of particles on each side, just exactly one particle on each side. Okay. So we're going to take this term in here, where SI² 0 to beta, tau. Do the same thing on every site. So I'll drop the site label for a minute. S squared. This I'm going to write as integral of some auxiliary field I'll call phi. It's a vector field, and it's basically the spin density on site I. It's a conjugate to the spin density, but I want to focus on the effect of magnetism, exponential minus dropping the site label d tau 3/8u phi squared minus phi I dot into C dagger I alpha sigma beta 2 C. There's a overall normalization, and that's an exact identity otherwise. All right, so what I've done is I've taken this operator that's quartic in the spins and decoupled it in the spin channel. So it's C dagger sigma C. Now this, the BCS3, we did almost exactly the same thing. Okay, I've erased it. You had the same Hamiltonian with the J term, and we factorize it into C dagger C dagger. Now we factorize it into C dagger C, because our interest for now is the effect of magnetism in this metal. Later on, we'll have to work harder to do fluctuations to figure out the effect of pairing. So, I could have just started with the Hamiltonian and just replaced this operator SI squared by expectation value of SI into SI. I could have just done that, maybe an effect of 2 here. And this will be the Hartree-Fock approach. And this SI basically is the effective, is the thing we're calling phi now. And the reason I'm doing this, well, you can do that if you wish. And but I'm trying to be more general for a little bit longer. This phi I is basically the expectation of SI, but it's a function of space and time. At the moment, I also have fluctuations about mean field in our theory. If I do a saddle point calculation where I just replace phi by a constant, then that's equivalent to, similar to actually, not exactly the same as the mean field theory. But since I'm interested in corrections, go beyond mean field theory, I will do it, I will be exact for a bit longer. All right, so now if you take this object and you plug it in here, as far as the fermion determinant is, fermion integral is concerned, it's just 3 fermions. So formally you can write it as a fermion determinant. Don't worry if you don't know what that is. In any way, so I can just rearrange these 2 terms and write the following action for the path integral for Z. So just by some rearrangement. So without any approximation yet, so I'll just interchange the order of integration, d phi I of tau, exponential minus d tau, 3 over 8u phi I squared. This is a real vector, plus some, let's call it S effective. Well, it's a Lagrangian here, L effective, which depends, which is a functional of phi I of tau. And then this. Okay, so we have separated the problem into 2 separate pieces. I have this boson phi, which henceforth I'm going to call the Paramagnon, because that's what it turns out to be in the end. It's para because you can even talk about it in a phase where there is no broken symmetry. If you break the symmetry, then it becomes a true magnon. But we are going to try to look at fluctuations of phi, and historically it's been called the Paramagnon. And it also has some lifetime, which is the reason for the word para. So there's a Paramagnon field, which is just acts on the spin density of the electrons. So what we have to then figure out is this Lagrangian, which is the the partition function of the electrons in a time-dependent magnetic field. It's just free electrons with some dispersion and a time and space-dependent magnetic field. Okay, this is still a very hard problem. And in general, you can only evaluate the right-hand side by expanding in powers of phi, which is what we'll do. But some simple cases you can do better. And I should also say you can do exactly the same thing for superconductivity. This would look very similar, and this would be the Landau-Ginzburg action. And with superconductivity, you would have a C dagger term. And my comments to Juan's question earlier had to do with, when is it valid to take this object and expand it in powers of phi? And how should you do that expansion? And the point is that the nature of the expansion is very different at 0 temperature than at finite temperature. Because a non-zero phi to begin with completely changes the fermionic dispersion. All right. So with all those caveats, let's just go ahead and expand in powers of phi. Imagine it's a high temperature and phi is small, and we just look at the second order term. Okay, so.
Subir, which limit of the model are you considering? This is with the finite magnetization, antiferromagnet?
At this point, everything's exact. It could be anywhere in the phase diagram. I haven't done anything. But the next step, where I'm expanding in powers of phi, I am making an approximation. And I'm just asserting that that approximation may be reasonable at high temperatures. Let's just imagine that we are at some high temperature and we're going to expand in powers of phi.
But you need a non-zero value of average of SI, right?
Well, if phi has a I still have to do, there's two steps. First, I have to determine L of phi. Then the next step is to do the path integral over phi. And the structure of L of phi will tell me whether phi has a non-zero expectation value or not. So it will have some expectation value which could depend in a complicated way on space. And in fact, we'll find that there's some regime of couplings and Fermi surfaces where it has exactly the same structure as an antiferromagnet. It has opposite orientations on different lattice sites. And then you'll be in an antiferromagnetic metal.
I see. Thank you.
But at the moment, I'm totally general, at least for now.
Okay.
No approximations. This is just a rewriting of the Hubbard model. Okay, so now I'll just look at the first approximation I'm going to make is to expand L of phi to order phi squared. I still, even after that approximation, I have to do the path integral over phi. So, okay. So I can drop the effective, but all right. Okay. L of phi. Well, what is it going to be? Well, first of all, there won't be any linear terms because of spin rotation invariance. It's a vector in spin space. And the rest of the path integral is invariant in the spin rotation, so there's no linear term. So the first term will be quadratic. And what does it look like? Well, you can just expand this out. Diagram that you wish. You have a phi here with a C dagger and a C. And another phi here with a C dagger and a C. And there's a sigma Pauli matrix here and a Pauli matrix here. And then you have to do the integral over C. That you can do using Green's function. And you can see that the only thing that's going to contribute is this bubble graph. Or it's the spin susceptibility or the Lindhard contribution to the spin susceptibility. Okay, so L of phi has two terms at order phi squared. Let me also get my factors of 2 correct. Turns out to be 1 over 2 Q and omega. I'm going to go to Fourier space phi of Q and omega squared. P over 4u minus quantity I'm going to write chi 0 of Q and omega. I omega there because I'm working imaginary time times this plus various things. And chi 0 is this graph. So chi 0, this has momentum Q and omega coming in, Q and omega. So this will have K plus Q and plus omega. And this will be K and epsilon. So if you write down this graph, there's a -1 for the fermion loop. And you get minus sum over P I of K and epsilon. And now you take the free fermion Green's functions, I epsilon n minus EK, I epsilon. Okay, and so when you do the frequency summation over epsilon, this becomes the Fermi function EK plus Q minus F of EK over omega plus epsilon K minus epsilon K plus Q. Sorry for writing it so small, but actually let me write it about big because it's really the key thing to all the subsequent discussion. Let me put it up here again. Over K, F of K minus F of Q, or I omega plus K minus EK plus Q. This is a very famous function in condensed matter physics. It's called the Linhart function. It usually appears when you compute the dielectric constant of metal. Here I'm looking at the spin response function rather than the charge response function. That the fact that a spin has these Pauli matrices, and you trace that over and it gives you additional factors of 2 or 3 somewhere. And the minus sign also is related to the fact you're talking about spin rather than charge. Okay, but this function we now have to evaluate. It's a basic property of any metal. The response to either a spin or charge density to linear order at frequency omega and the momentum Q. Or another way to say it, suppose you have a metal sitting there and you put a space and time dependent magnetic field, Zeeman field on the metal. Then to linear order, the linear response would be a spin density. And this is the linear response function. So if you apply a magnetic field, Zeeman field H of Q and omega, then chi 0 determines the spin density average in the presence of the magnetic field of the electron, free electron gas. Similarly, a dielectric, this is really the thing that appears in the polarizability. If you apply an external potential, you get a response to the charge density of the electron gas, and then they're all determined by this Linhart function.
Sorry, can you repeat where the first term comes from? The one without the linear response function?
This one?
Yeah.
That's the 3/8, the phi squared term.
Oh,
That came from Hubbard's trigonometry.
You're writing the full Lagrange now.
Yes, yeah. All right, so if you look at this function, it's very unfamiliar to particle physicists, but it's just this one loop diagram for the, and if you have Dirac fermion, it's something exactly what you expect it to be. But for a Fermi surface, if you're a little more careful in evaluating this. So this is a gapless system. So EK or EK plus Q vanish on the Fermi surface. So there's some metal that we're dealing with. Okay, so this is the Fermi surface. And what the numerator tells you is you're creating a particle hole excitation. So the initial state and the final state better be opposite in the occupation. So for example, you can take an electron from here that's occupied and move it to an empty state. So this would be momentum K, this would be K plus Q. And this momentum Q is given by your external perturbation. Okay, so f of ek plus q is 0 and f of ek is 1. So you get a 1 in the numerator. And so, this is allowed. But if this last state was inside the Fermi surface, you get 0, so you don't ignore it. You ignore that. So you're always taking states from inside to outside or vice versa. And then let's look at the static response function, where you ignore this omega dependence. Then there's an energy denominator there. Both of these vanish. This curve here is the curve ek equals 0. And you can draw another curve depending on the wave vector q. There's another curve somewhere depending on q. This is the line where ek plus q. Okay, so then you have to look at, complicated integral as a function with all these zeros of the denominator and also the Fermi function in the numerator. Okay, so that's not a pretty sight, and it takes some work to evaluate this. But the general rule is that you get a huge enhancement of these correlations when you have something called nesting. So these contributions turn out to be very large when you have nesting. So let me just illustrate what nesting is. Things kind of look quasi one-dimensional. All right. Maybe I'll just draw this figure again. So consider the following situation where you have some Fermi surface and maybe it has some flat portions. It's not exactly flat, but almost flat. So you can see, draw better. That still have the square lattice symmetry. Okay, so this is the original Fermi surface. And imagine you take a wave vector q, which is here. So what's happening is this is ek equals 0. This wave vector is q. This is your q, and this line is ek plus q equals 0. And what's happened? So these two, the initial and final portion of the Fermi surface are nested here. So they're just touching each other over an extended region. And depending on exactly this, the way they touch each other, then at this special wave vector q, you'll get a huge enhancement. This thing will become large. So it's a matter of, in general, it's these integrals are all finite. There's no divergences, at least in 2 dimensions and higher. And because the nesting is never always exact, it's now actually a straight line. And so then it becomes a complicated matter of finding what's the value of q for which this is a maximum. Now, why do we care about maximum q? Well, because we see here that when this q chi naught is large, that's when phi will have the least energy cost. That's where, and in fact, when this object becomes negative, then in the simple theory, you would say phi will then condense. You get a Mexican hat potential, and you'll have to worry about the phi to the 4th terms on that involves more complicated expressions like this to get the coefficient right. But what you notice that these coefficients here depend sensitively on the nature of the fermion dispersion. So if I was to answer, there's an analogous question to what Juan was asking, answer question on the nature of the fluctuation in the condensed phase. So when you're in the condensed phase, in this case, you could have analog of a Higgs mode or a spin wave modes. You'd have to recompute this whole expansion because once you condense and you put phi, so when you condense, you write phi is phi some constant plus some delta phi. Well, this condensed part completely changes the fermion spectrum. And so all of this expression becomes completely different. All this nesting disappears and so on. And so what you shouldn't do, and this is the dangerous part, suppose I get this theory to order 5 to the 4th. I say, yeah, that looks great at high temperatures. As I lower the temperature, this quantity becomes negative. And then I go in the condensed phase. And then you start using the same energy, same free energy in the condensed phase. You should not do that. That's the most dangerous part. Because what happens once phi condenses, even the sky changes in a singular way, because the Fermi surface changes.
Sir,
Yes.
can you repeat the last part?
Yes, sure. So that's a subtle but important point. I'm jumping ahead a little bit. So let's imagine we can do this naive expansion in powers of phi. And I get this, I compute this, and I even compute 5 to the 4th. And then you say, oh, well, that looks great to me. Now I just have a 5/4 field theory in my top path integral, and I'll just look at all of its properties. I'll find out the critical temperature, that's fine. And then I'll go below the critical temperature where phi condenses, where phi has some expectation value. And then I look at the fluctuations about the condensed phase and look at the poles of the propagator of delta phi. That will tell me about spin waves and Higgs particles and other things like that that appear in a condensed phase. And the temptation will be to do all of that in the 5/4 field theory that I just obtained with the complicated Q and omega dependencies you have here. The 5/4 term also depends on a complicated way of Q and omega. And all I was saying is that that's not what you should do. And the reason is, very much has to do with these Fermi surface singularities. Once phi condenses, you have to recompute this expansion in delta phi and keep the dependence of chi naught on phi, the condensate, to all orders. You cannot expand the dependence of chi naught on the condensate because that has a singular effect. This condensate will appear in the denominator, will change the dispersions here. That is really important. I think there are similar issues in particle physics with the chiral Lagrangian only works in the confining phase, but that doesn't mean you can do that chiral expansion in the deconfined phase. Okay, so did I answer your question?
Yes.
Okay, great. All right, so let's just do the very simple thing. We won't worry about dynamics. We'll worry about condensing phi, just finding the critical temperature. So now there's a simple guess, which is, in fact, the same answer you will get from mean field theory. You could have just done the usual mean field theory and you get the same answer. So you will now conclude that phi, so here's the statement I'm going to make. Phi I expectation value will be some vector, let me call it n, times cosine of Q max times R for T less than Tc, where Tc is determined by, well, exactly the point where this goes to 0, 3/4u equals chi 0 of Q max at 0 frequency over 2. And what is Q max? Q max, I don't know how to say this in mathematically elegant notation. Q max is, well, it's a point at which is Q, which maximizes any given temperature, chi of Q and 0. You compute the function chi of Q and 0, it'll be some function as a function of Q in the Brillouin zone, and you look for where it's a maximum. As a function of Q, pi of q. It'll have some shape, and this will be q max. The q max will be this kissing point typically, where the the shifted and the original Fermi surfaces kind of tend to nest with each other. So there's a new wave vector that emerges. The lattice scale emerges here by determining this wave vector q max. So phi sub I can have a very complicated dependence on R, but the assumption here is that the very rapid dependence is here. And then to understand the condensed phase, this n can have a slow dependence. So there's a rapid dependence that comes from the maximum value of q, and then everything else very slowly.
What is the index I versus R?
Thank you. It's the same. And everything is independent of time. The condensate is time independent and will condense at some wave vector. Okay. So this condensate is what's called a spin density wave. And if the wave vector is some arbitrary wave vector, people call it incommensurate spin density wave. It's some rational wave vector like pi, then it's called a commensurate spin density wave. And the antiferromagnetism I'm referring to is its q corresponds to pi. So we're just going to assume the Fermi surface. So this is an assumption, which you can, well, I don't know. You can say it comes from experiment or it comes from some dispersion relation of your favorite Fermi surface, and so on. But let's just take the simplest case. In 2 dimensions, we assume q max equals pi pi. And that will give us antiferromagnetic metal. And we'll try to conclude today by just saying a little bit about what is this antiferromagnetic, what do the fermionic excitations look like. So the steps is we've computed chi naught, we figured out the q max, and then once you're condensed, I want to go back and look at the electrons. What are the electrons doing in the presence of this condensate of the spin? Okay. So what is the electron Hamiltonian? Let's go back to the Hamiltonian language. The electronic Hamiltonian was epsilon k c dagger k alpha c k alpha minus in real space phi I. What did I call it? N, right? We'll take n to be in the z direction. Let me make it n here with n constant. We'll ignore the r dependence of the n because the condensate is exactly at pi pi. So the n times e to the I q max by r. Because of e to the I pi is -1, so I ignore. Well, okay, let's make it cosine. What should I? Cosine of q max. That's r times c dagger r, and let's say it's only in the z direction, alpha sigma z alpha alpha c r. So this is the spin density of the electron on site r in the z direction. I made n. No, I guess let me be consistent. All right. Okay, so I have some condensate vector n, and it has some cosine dependence, which comes from q max, and beyond that, it's a constant, and then this is the spin density. So this is the spin density wave Hamiltonian, and it's the complete analog of the BCS Hamiltonian, many other things we've met. The BCS Hamiltonian had the free electron dispersion and something that couples to C dagger, C dagger. That C dagger term broke number conservation, and you diagonalize it by a Bogoliubov transformation. Here I'm breaking spin rotation symmetry and also translational symmetry in a complicated way that's determined by the wave vector Q max. And then I get a term which is the modulated spin density times the spin density of the electrons. So that's the theory of the antiferromagnetic metal. It's got the condensate of the spin density, and then the fermionic excitations have the following effective Hamiltonian, and that changes their dispersion. So now I'm diagonalizing this. So this is going to be, exactly the way we did before. It's going to turn out to be some K, some EK, C dagger K, some gamma dagger K alpha, gamma dagger K alpha, just as before. But here it's even simpler. You don't have to do a Bogoliubov rotation. It's just reduced to diagonalizing a 2x2 matrix, which we can do very easily. And then you write it in terms of the fermionic excitations about this state that breaks spin rotation and translational symmetry. And that's what an antiferromagnet is. So this is, this wave vector, that's exactly, at least as far as the broken symmetry is concerned, it has the same structure as the insulating antiferromagnet, but the fermionic excitation is completely different. Yeah.
Does this EK, can it depend on alpha? Because
this one?
No, the one below, because you broke the SU2 symmetry.
Yeah.
Expectation value of N. So why is the last?
Right. Okay. So let's put N in the Z direction. Then there's still some kind of, yeah. Okay. In general, it can, sure, but in the case we're considering, it won't. All right. So now the task is just to diagonalize this. And let me at least set it up a little bit. So the tricky part here is this R dependence. When you go to Fourier space, that simply means that you shift the momenta here by Q. So what this becomes, and let's take it in the Z direction. So we take N 0, 0, N naught. And this thing is simpler for this case. Otherwise, this becomes a very complicated mess in general for a general Q. But you can write this something like C dagger N naught.
So be the second term in the spin density wave, is that proportional to phi squared or phi?
This one?
Yeah.
It's phi. I'm sorry, I erased that. There was a term phi times C dagger sigma C in the original electronic Lagrangian.
I see.
So what I've done is I played a trick where I told you I'm integrating out the electrons, and then I get some L effective of phi, and then I've worked with L effective of phi, and I found some constant phi, and then now I'm going back to the original electrons, which I had integrated out, and looking at what the effect of the phi would be on those electrons.
I see. Okay, thank you.
Okay, so this would be C dagger K. K alpha, I believe sigma Z alpha beta, C K plus Q max. So it basically scatters the electron from momentum K to K plus Q. Now, the nice thing about this Q is that 2Q is the same as nothing, is 0, because of pi pi. So that's why you can just sum over all K. But if you have some other wave vector, then you get a very huge, you get K mixes with K plus Q mixes with K plus 2Q, and so on. You can still get an infinite matrix to diagonalize if Q is incommensurate. And some of this mess happens, in twisted bilayer graphene and things like that. So it then becomes a messy thing to probably understand when you have incommensurate potentials. But for the commensurate case, like pi pi, it's very simple because K plus 2Q is the same as K And then you can see it's just something very simple like this. All right, so this then you can, for this case, reduce everything to a 2x2 matrix. But the general Q case, which is incommensurate, it's really an infinite by infinite matrix that you have to truncate in some reasonable way. All right, then I'll write this out more explicitly next time. And we will, I think, I'm on track to finish our discussion of antiferromagnetism and D-wave superconductivity on Wednesday. Yes.
So I'm confused about the role nesting really played. Nesting seemed to provide a large enhancement,
Yes.
but then we have to correctly analyze the fermions in the presence of the condensate, whereupon there isn't that enhancement anymore.
Right, so we're imagining coming down from high temperature and looking at the initial instability. Now, it could be that as you went into the condensed phase, that the wave vector would change. So we're just looking at the first, just on.
So the discussion of nesting made sense when the order parameter was just turning on.
That's right. But you could, at lower temperature, have a transition to a commensurate. So there's something called an incommensurate commensurate transition that happens in many systems where initially at higher temperature, you see a nesting wave vector, but as you lower the temperature, it prefers to just lock to the lattice and be something commensurate like pi pi. Yeah. So all of that would require then doing a much better job of the effect of exactly what we're doing here. Doing this for general Q and recomputing chi naught in the general Q. But I guess I would say that at least for the cuprates, this nesting argument, there's no evidence it's correct. Cuprates are in a strong coupling regime. If you really took them, given dispersion relation that you measure from photo emission and computed chi naught and got Qmax, it doesn't agree with anything you see in the experiment, really. Maybe the nuclides it does, but the cuprates, there's little evidence of that. So this is intrinsically a weak coupling argument. Other materials like chromium, apparently, it works extremely well. So here I'm just asserting that there's a condensate, and I don't ask too much of where the condensate came from if I want to apply this to the cuprates. Because this is all, an expansion in powers of U ultimately, and that doesn't apply. Yeah. Fortunately, in the cuprates, mostly you see, you do see some incommensurate wave vectors, but at least in the electron doped over a wide regime, it's pi pi. So let's just consider the simple case for now. There's no fundamental difference between other Qs. I mean, they're just more messy. Okay, great. See you on Wednesday then. Any questions in India? All right, so
One question.
Yes, go ahead, please.
Is it easy to see that if the size of the Cooper pair is large,
Yes.
it is beneficial to put all the Cooper pairs in the zero center of mass state? Yeah. And if it is the Cooper pair size is small, I cannot it won't be energetically favorable to put all the Cooper pairs in the zero center of mass state.
So there are possibilities of superconductors not in the zero center of mass state. These are sometimes called the FFLO states. And they typically require pairing between electrons with different sizes of Fermi surface. You just had, we're talking about zero magnetic field and an electron dispersion spectrum that has inversion symmetry, then almost always the zero center of mass state has a lower energy. Experimentally, there, I think, a few reports of FFLO states, maybe in cold atom system, they're quite hard to find, but it does require unequal Fermi wave vectors. Now, I think in the in the QCD plasma, high density QCD, there are some states of that type that people talk about a lot. And that's because the number of off-dominant space quarks have different densities and so on. But if you have equal number of spin up and spin down, which is what I'm assuming here, then you won't get this kind of Cooper pairs and non-zero wave vector.
Hello?
Like you, Al, you worked on some of these QCD plans, or no?
No.
Okay. Yes, another question.
So I wanted to ask that you said the nesting enhances the Linhard function.
Yes.
Yeah. And is that the case that Qmax is a nesting wave vector, because nesting is a condition for charge density wave formation?
Yes, yeah. So in fact, if you have exact nesting, then in fact, chi of Qmax diverges. It diverges logarithmically. So in 1D, chi of Qmax is log of Q minus Qmax. But that's only if you have exact nesting. In 2D, there is no divergence. There may be some singularities away from Qmax, but it doesn't diverge. Yeah.
Okay, thank you.
I mean, the log divergence in 1D is, very closely related to various logs in the Gross-Lebeau model in 1D. Relativistic fermions is the same thing. This is just generalized to higher dimensions. Okay, so see you on Wednesday then.